Yeah, we're lucky to have John Myles White coming in from Princeton as a guest to show off some cool data frames things.
Hi, everybody. So I'm actually going to sort of be the first talk that's focusing on stuff built using the package system. So it would be really great if you ran these two commands in your Julia installation to grab your first two packages.
And if something goes wrong, should they tell you?
Yeah, well, tell me, and then hopefully we can get someone who's not me to come run to your computer and help you get it working.
So yeah, if it doesn't work, don't be shy. We have a very large faculty.
But so there are basically two packages here. One is like totally essential to following along to the talk, which is getting package.add data frames, which will install the data frames package, and its dependency, which is the options package. Those are really essential to doing the talk. The RDatasets package just makes this much more interesting and much more exciting because it pulls in a repo that's full of about, say, on the order of 600 CSV files that are all the canonical data sets that come when you install R. And so it's just really nice to have these things to work with. I think Doug also tomorrow will be talking about statistical modeling is going to use those data sets to show how you would do some models with them. All right.
I'm just sorry.
Oh, no worries. So hopefully this works. If it takes a second, that's fine because we'll still sort of be talking for things for a little bit before we have to use it. But it would be good to get it going. Then I guess we'll go back. And yeah, so having. Yep.
Sorry.
No worries.
What happened there?
There we go. Okay. Yeah. So.
Next slide.
This is good right now.
Okay.
So having added data frames and then adding our data sets, you can just now pull in these packages using the data frames, using our data sets. And people mentioned this before for calendar, which is one that's going to actually do a require and load these files into main. And then in addition, it's actually going to give you access to the namespace things. And there's a bunch of stuff that you're going to want, especially the data frames. It's going to fill your namespace with quite a lot of different functionality. Can we go on that? So the very first thing I want to think about is how do you cope with missing data? And this is actually something that Julia, I think intelligently, was very much designed in a way that makes it not obvious what you want to do, which is so to move on to the next slide. And so the very obvious case is just this one. And you can talk about more sophisticated cases, but imagine I'm going to build some vector with 5 entries, x1 through x5, and I want to compute the mean of it. Well, how much can I do this and what cases is going to work? Well, it's definitely going to work in the case where these are all floating points. Normal Julia totally handles this case really nicely. But if you go on to the next case, this sort of thing really is not expressible in Julia. And this is what the data frames package starts by building in and then moves on from there and gives you what I'll talk about later, which is basically like a relational database in memory. But the core thing is this NA type. And it's the idea that you might have 5 values, but you actually might not know one of them. And this is, in practice, my experience with everything you ever care about is that most of the data is missing, and there's just a few things you actually know something about. And so you need some way of expressing. Can we stop it?
Okay.
It's like on auto.
No,
Yep.
it was me.
Oh, OK. Well, thanks. Yeah, I may not get through all the slides, but we'll see how far I go. But the basic object is this NA type. And so it's going to represent a missing value. And this is something like null in, say, Java, or if you've used R or a language like that, they have an NA type, which is meant to be not available data points. And this is something that Julia intentionally decided not to have, that you would not be stuck in this position where sometimes someone's going to pass you back something, but it was actually null, and so you couldn't do anything with it. And so we had to basically go back and retrofit Julia with this concept of having a missing value, and that's what NA stands for. And the other special thing about NA is that it's poisonous. And so that's what the next slide we'll talk about. But like NaN for floating point numbers, it's going to just corrupt every computation afterwards. And so if you can see on the next slide, you do things like 1 plus NA. And you can just put this into your Julia REPL. If you've got data frames loaded now, you'll see that this hopefully will work for basically any basic operation you might want. And we have to actually basically redefine all these things. Yeah. So we have like 1 plus NA. You're going to get that, and that, like doing 1 plus NaN, is going to corrupt it and give you NA back. OK. Yeah, so you have 1 plus NA is NA. 1 is greater than NA, also should be NA. And then in order to cope with the fact that you're going to now get all these NAs everywhere, we add a new predicate, which is NA. And if you do is NA, yeah, so you also equality works this way, which is why you need to have is NA as an additional predicate, because NA equals NA is unclear. And this is, if you're not used to doing statistical programming, the logic of this may not be obvious to you, but this is, this is something that's missing, and this is something that's missing. There's no way that I can tell you whether I actually know that those things are equal. And if I were telling you that, it would be a horrible idea. And so that's why we have to have this additional little NA predicates.
So it's just like in floating point, right? Like,
well, no, because not a number is equal to not a number or is false. We actually, yeah. I mean, it's similar, but it's always false,
right.
But it has a well-defined truth value. Here we have a missing this value in placing. That's because the thing is, unlike not a number, which is sort of this concept of equality doesn't make any sense. The concept of equality might totally make sense for things that are missing. It's just that you don't know whether they're there. But if you had imputed them correctly, maybe they would be equal. So this is sort of the core basic operations, and we have to do a bunch of this stuff. So this is this slide, and you can move on, and then really what you want to do is have to be the ability to have lots of nice, efficient data structures for storing these things. And this is also if you're coming from a language like R, but also things that have been built into languages like Python now. So there's like pandas, this toolkit that's very similar, very similar to R's functionality. But for Python, you want to have these things like vectors and matrices that store NAs. And Julia actually, once you add the NA type, is totally capable of doing that because you can use these cell arrays that you make with curly braces. The problem with that is that you now pay a pretty noticeable penalty for doing this because everything is pointers. So what we do is we add this data array type, and it basically just sort of extends the array type, but I don't use that word extends in sort of an object-oriented sense. I mean, it's like a complement to the array type that sort of mirrors it in a parallel universe of Julia. But now suddenly a data array whose parameter type is t can store either things that look like t, which might be, say, a floating point value, or they can also store this new value NA. And this is the only additional thing. And we actually get this under the hood by actually having all of the original data stored as an array, and then side by side it, there's actually a bit array, which is a single bit for every value, which is this thing NA or not? And so that's how we actually get this is sort of the lowest, cheapest way of expressing NA.
so what's the type of NA?
NA's type is NA type.
It's NA type, okay.
Yeah, so we add a new type called NA type, and then NA is a constant value, which is like a singleton of that class.
Should we see that? Or?
Yeah, let's do that. I think that's useful. Yeah, so type of NA is this. And this is, the way you did it is that you just did NA type, and then you made const is effectively what happened. There's a Julia keyword for constants, which is NA is this constant defined to be the one instance of this type. And so now you have this mechanism for storing all these things. So that's what data array is. So if we move on to the next slide, you'll see some computations you can do. So the one thing that's a little unfortunate and sort of, I think over time we're going to think more about nice ways of making these things, is that what you do to make a data array basically is you take an array you already had and then construct it by wrapping it in this constructor. So you say, dv, which would be my data vector, and that'll be a data array built out of an existing vector that I then sort of bless to be a data array. And then after that, now I can start doing things like adding NAs into it. And so dv of 1 equals NA now assigns NA. If I use this join function, which is just a general way of doing string joining by interpolating values, which is what these two colons are doing, are being interpolated in, this thing runs on data vectors, interpolating correctly NA, where I inserted it in the first value, and then inserting the 2s and 3s everywhere else. So very simple stuff. So we can move on. You can get lots of things like this. So Julia has zeros, ones, falses, trues, diagam. These are all functions that sort of come from the MATLAB heritage, and we've just cloned all of them. So if you conveniently want to have a big data matrix, you can do data I, for instance, and now you'll have a giant matrix of, say, dimension 10 by 10. Let's just start there. And now you can actually insert into this thing, say in the first value, an NA, or anywhere you want an NA. And actually, let's do that. So just to sort of make it clear to people, you can play around with it. So let's make a data I 10. And say A of 5, 4 equals NA.
Okay.
Yeah, or 5, 5, it doesn't matter. I mean, don't. And now do A times A. and you'll see the correct propagation of NAs through everywhere. So this is poisoning all the values that are appropriately supposed to be poisoned.
Can we see like say for 8 times 8, can we see what was sort of underneath and the bits as well? Or?
Yeah, definitely. So the pieces of A are a.data. I'm a little hesitant to try using the dump function, which might work, so let's just do it manually.
But if I say star, will it now have a method for doing multiplying data?
Oh yeah, definitely. So if you do star, you'll see we add a bunch of stuff in here.
It's,
You know,
it's almost there.
which one?
Kind of, yeah.
Is that the one that's highlighted?
No, the one that's highlighted is that there's almost certainly an actual data array times data array somewhere. I'm not quite sure where.
It could be in a really different place.
Yeah, I mean, star
It's
is.
got to be somewhere here.
I mean, there's data array times number. I mean, it's, you know, if you want to search through it, you'll find it.
It's a
It's,
slightly nicer way to print these. This has a
Yeah.
personality of its own.
you could grep it, yeah. You can also do, you could do a which. You can, we didn't really talk about that, but you could do which star AA. Well, this is actually probably, this is certainly the way I would do it. Yeah, so this is how you're going to find out what's being done. So this tells you that there's a star method. It's a parameterized by S and T, which are both inheriting from real, and it has 2 arguments, a data array that's 2-dimensional of reals, and a data array of 2 dimensions that's also reals, and it's defined at this function, operators.jl. And this operators.jl, I think, is sort of one of the coolest things about Julia is that this file is just an enormous amount of metaprogramming that implements all of the things that are in base Julia, again, to correctly work with NAs. But I think Alan's question is also really interesting, which is showing you the sort of under the hood. So if you do a.data and then a.na should show you what you really care about. So that's a.data. And so this is actually what's happening underneath the hood. So the way we get everything is that we take the original matrix and we append it with this bit array, and the bit arrays tell you which things are NAs. And then we can easily and very fastly propagate NAs through computations this way. And actually, like that's, for instance, the multiplication step is in fact being done, which is we take the multiplication of the underlying data and then post hoc do all the NA computations because they're way faster that way.
Jeff, is this going to work? If I do this and go to line 185 roughly,
You can do this.
There's
Or
probably
no?
an even faster way to do it, but yeah, no, I think
Sure, let's do it. I mean,
that'll work.
I-
just to see the star.
yeah, this may be fairly opaque. So the way we did this is that there's
Terrifying.
tons of categorizations of functions in Julia, and then we redefine all these functions.
But you can basically just go there and find this, and this is the matrix multiply.
This is the matrix multiply. This is, you know, with a link to a blog post by Radford Neal, a statistician whose claim is that we should not even be bothering to do this. The propagation of NAs is pointless.
Like an existentialist sense?
I mean, he makes an intelligent point, which is, and so one of the complexities of, as I've said, sort of data arrays are basically mirroring all the arrays in Julia, and so in some sense we have to redefine everything. And so we did, for instance, there is like, which is really hackish. I like it because I like the algorithm being used, but if you do A, if we go back and we go back to the terminal, yeah, like A has a missing value somewhere now, yep. If you do SVD of A, this actually works. And this is because we're using this sort of EM style algorithm to impute all the values. You know, and this is like, you know, what is it you want to do? There's a way to turn this off so you get things without imputation.
I said correctly as it turns.
Oh yeah, no, for simple things, this imputation technique works quite well. I mean, yeah, so that's just sort of give you some sense. But so, you know, the argument against these things is how many of these things do I really want to do? Do I like want to re-implement FFT now for NAs? Like, what, you know, is this an intelligent thing? No, we didn't do that. And, you know, and you know, I think Radford Neal's claim is that maybe sort of at some point you don't want to track it. But to my mind, matrix multiplication is something we really do have to track. So we did track it.
You could do FFTA dot whatever data, whatever it was. If you wanted to throw out the NAs.
Yeah.
Oh yeah, you can always.
So you definitely, yeah, so you can do that. And we actually, to show you another way to do it, you can do matrix of A and then do FFT of that. And so I'll talk more about this. Oh, Okay, this is going to fail because there's an NA. There's an NA in it. Yeah, so you actually don't want to do this because this is, I mean,
That's the cheating way.
this is the cheating way, which is,
Puts a number, but maybe
yeah, it's whatever, I mean, basically what happens is we just sort of arbitrarily grab memory to store
Right.
data, and
so
if,
whatever happens
and
to
so,
the-
yeah, and so whatever's there is what's there in the NA values. And yeah, it happens to be just for the case of matrix multiplication. Maybe this is also true of FFTs, but I'm not aware of it. For matrix multiplication, you can easily know without even looking at the values which things are corrupt. And so,
Maybe if I just do data frames.matrix, will it work?
no, the problem is that the conversion of it to a matrix doesn't make sense because it hasn't.
FFT, everything's gonna be NA.
Yeah, that's so. Well, so we can define that easy. That's a
That's the
particularly
easy one.
particularly nice one to define that we'll get to. But so let's sort of move on. But this is to give you some sense of what's happening. Here's tons of ways of constructing these things. Yeah, no, let's keep going. So this is showing you when you do the SVD in a case where there are no NAs, and in that case we don't have to do any black magic. Move on a little bit more. There's also a thing which I think is quite useful, which is, and this is data in, data float, and bool. And Julia has these like int, float, and bool functions, which will take an existing array and do conversions element-wise. And if you show this one, this is nice. If you go to the next slide, you'll see an example. So you have, an existing float vector in Julia, and I want to make that into an integer date array. And so this data int will do this. First, it will make it into a data array, and then it will actually do the integer conversion. And that's actually, the order of operations is actually the other way around. It first converts integers, and then makes a data array. And the same way with data bool. So these are actually, I think, probably more convenient in many cases for building these data arrays if you want to. But let's keep going, because in some sense, the really thing that matters is thinking about other sort of powerful techniques. So one is this idea of storing data more efficiently. And I'm going to go through this kind of fast, because it's, I think, probably really opaque if you're not used to R. But R is really interested in this idea of thinking, how can we store categorical data more efficiently? And in addition, the sort of magic treatment of categorical data in statistics. And so what we have is this idea of a pool data array. And this just compresses the data array. So let's just kind of flip through this fast. So here's one way of making a pool data array. A bunch of different strings, but they're repeated. And so the idea is, well, we know they're repeated. We could just store pointers to the values they take on. So make a pool data array. We can assign it to it. It's going to look a lot like a data array. We'll go to the next slide. But when you do this levels computation, it's going to tell you all the values that it actually takes on. And basically what's happening is that there are a set of unique values that can happen in this pool data array. And then every value is a pointer to one of those levels. And the next thing gives you the underlying hood magic if you care about it. So what happens is that a pool data array is actually just a bunch of references, which are 16-bit pointers to things, and then the pool. And they have the magic property that 0 always points to the NA value.
Why don't you use 16-bit pointers when you get away with 2 bits and strings?
So because we didn't do an intelligent way of adapting to the data, so that's what's happening. Right now what we're doing is 16-bit. There is a way very easily to change the parameter, but actually doing it intelligently is something we have yet to do. Probably one day we would like to do it. We certainly want it to
It may also end up being too opaque, so there's like.
Well, I mean, I'm not so worried about opaqueness. It's just more computationally intensive. What we probably will eventually do is do an automatic overflow detection, and then if you actually overflow, then we expand the thing. That's, I think, the long-term goal, but we haven't quite decided that yet.
Okay.
So that just gives you a sense. I think actually the thing that's really cool is thinking about heterogeneous data. And this is something that if you're not used to is sort of not obvious why you care. And this is what I mean by heterogeneous data. So it's a table of data. And in some sense, this is fundamentally unlike an array. It looks like a matrix, but it has very strong properties. So one is every column has completely homogeneous type, but every column across things is completely heterogeneous. And in addition, the columns have to be data arrays because they need to store the possibility that data is missing. So this is my hypothetical data about some people, John Smith and Jane Doe. We can move on. And the question is, how do you build that? And in Julia, now you can build this by using a data frame object. And if you, yeah, definitely. So if you've never seen a data frame or language with something like this, the way to think of it is it's like a very simple implementation of your standard relational database in memory. It's definitely less powerful than relational database, but we're sort of slowly getting in that direction. But it has things that you really care about. So you make this data frame, you insert all of these different columns, and the columns can be done by name, and we'll also see by number. And then into them, we've inserted a bunch of data vectors. This is a sort of way tricked out way of constructing data vectors. which Julia has this magic, which is really nice, but a little opaque, which is that you can actually redefine ref, which is the function that uses square brackets, and you can define that thing on a type, and that can be a way of constructing elements of that type. And that's how we get the fact that now you can write literals that have NA in them. Otherwise, that's impossible because the square brackets otherwise have to be sort of strongly typed. So this is our basic data frame. Let's actually move on a little bit. So sort of the cool thing about it is, one, is the fact that you can even do this, and that's what it looks like when you do it. And then you can start pulling out things. And the thing that's nice about these things is that you can index into them like this, where you get just the weight, and that's doing by columns by number, or columns by name, or rows and columns. And the way to think of it basically is rows are still like it was a matrix. They're just numbers, that this is the first row or the second row, but the columns are now simultaneously the sixth column or the column whose label happened to be gender. And this is sort of very convenient for thinking about doing data analysis. So we can move on. This is a way of showing that you can do that. So you can build a data frame. You can create one column called A, and then you can create a column called 2. Right now we have the restriction, and I don't know whether we'll keep this or not, which is that if you wanted to assign numerically into a new column, either has to already exist or be the next column that would come up. You can't just like say, I'm going to assign to the 10th one and just fill a bunch of things, because it's unclear what we would fill in. So this is a very simple way of making a data frame. Here's a data frame again, and this is actually really worth knowing. If you do start using the data frames, at some point you're going to figure this out, which is that since we always need column names, we artificially generate them if they're required. So here you can see that there was a column called x2 inserted. And this is going to happen a bunch of times. But the cool, really, the magic of these things is that they now let you get access to basically like any spreadsheet that you have on your disk. So here what we did is we took a data set. It's stored in a CSV file that we dumped out of Excel because we don't have binary compatibility with Excel yet, but hopefully we'll get there soon. And then first we just generate the path, and this is the path on my disk for this thing. And then we use this function called read table on that path. And now we'll read in a data set that was a CSV data set into here. And you can see this is the head of it. The head is just the first couple of rows, and there's also a tail. Let's go to the next one and then pause there. And then tail gives you a couple of rows at the end. And so you can see is that you can just take some CSV file that you had, and now you can represent it in Julia very nicely. And what I mean by nicely is these things, one, have names. They're accessible using the names and by numbers like a matrix, but they're also properly typed. So these things are actually ints, these things are floats, these things are floats, and these things are actual bools. And this is really, really helpful for knowing that you're going to be able to do computations with types correctly. So this one way of, so this is just another way of indexing into it. So we'll skip past this one.
What is the difference between int and int-like?
Go back. Oh, int-like is an int. Oh, no, int, good question. Int-like is a bunch of columns that all could have been ints, but they were printed using floating points, and we decided that we would respect that. So if you put things as if they were floating point literals, we keep them as floating points rather than do an automatic conversion to ints. This is something that's definitely debatable, and definitely people have done different things in this.
Seems right.
It seems reasonable.
Yeah.
But so this.
The reader actually looks at the specs, all the columns to figure out what types are going to be.
Yeah, so what it currently does, and we may play around with this, but what it does is it reads the entire data set, has a bunch of rules for trying to parse lines into fields, and that turns out to be most of the hard work, is just figuring out, because CSV has quotation rules, has the possibility of embedding new lines and all that. We deal with all of that, but basically what it winds up doing is it produces this big array of strings in memory, and then column-wise we go through, attempt to convert them through a hierarchy of types, and the hierarchy is, if it looks like all ints, then keep it as ints. If it looks like it has to be floats, go down to floats. If it starts to look string-like, first see if it's Boolean, and if it's Boolean, keep it there, and if otherwise, go down to strings. And that's
a defect, and that is if I have a whacking huge data file that I want to process in some streaming manner, I'd rather up front just say, okay, this column is int, this is bool, this is character.
Yes.
Read it that way, but don't read the whole thing, just stream.
So there is a way to do it, but it's still sort of in process. So
But you guys are thinking about it, okay.
So it's actually like, it depends. The case exactly that you want is something that used to exist, was slightly broken, we turned off. So there is, you can do what it's called a data stream. I don't think I have anything discussion of this in the slides, but it exists. And the data stream will let you say, I want to pull in a mini batch of n rows at a time, and then it will figure out the types from that data. And what we are going to add is a way of forcing the types at every point. So you're going to pull in this mini batch and say, I assign these types every time. But we definitely have it. And it's actually quite, other than the fact that we don't have type forcing, it's generally quite nice already. So you can do things like pull in these little batches, and then with those batches, you can just do standard iteration over them. So more interesting is that if you also got this R datasets package, which I suggested installing at the start, and you're using R datasets, you can now do this iris equals data datasets iris. And let's try this and see if it works. And if it doesn't, let's do using R datasets. But so this will be the sort of a first dataset that you can actually really use that you might care about. Oh, great. So this is a 150-row data set that was created by Fisher as a way of describing various different algorithms for clustering and classification and so on. No, this is, oh yeah, let's go back to the slides. So this, now we've loaded in this iris data set, and you can do lots of really sort of interesting things with this. If you want to see all the other data sets, you can do rdatasets.datasets. You'll see that there are 570 of them. You can find out their names. And the way you load them is data, first name, second name. The first name is basically a category. What it is, it's the package in R that it came from. And then the second thing is the actual name of the data set. We do have docs that tell you more about these things, but basically, I'm going to use iris as much as I possibly can because it's just really convenient. Keep going on. So once you've loaded in iris, you can do things like col names to figure out what the names of all the columns are. You go on. You can do col types, and this is how you figure out what the types that were assigned are, and you can change these. Go on. Iris has an interesting problem, and this is because iris was carried over from R, and that they're called R datasets because these were all datasets that normally ship with R. R has lots of identifiers that have dots in them. Julia is not happy with that, so there's this clean col names function. So this is the col names. Now do clean col, clean col names, and now iris, well, let's actually do col names of iris. No, I told you to do that, so. You can see what happens is that they actually get made into correct identifiers. So this is a bunch of operations. The most obvious one, though, for our purposes, is just replacing periods with underscores. But there are other things like if things were all numeric, we're now going to put an X at the front of them so you can correctly use them. And the reason for that, let's start going back to the slides, is that another way that's really powerful of interacting with these data sets, and hopefully will be a slide or two.
Next slide.
Yeah, please. So this is some very basic stuff. So size, n row, and col. Let's keep going, actually. These are sort of a little bland. R bind, C bind, HCAT. These are ways of just joining things. Keep moving on a bit.
Is there a reason that you used R bind and C bind rather than HCAT and VCAT?
So we have all of them. And at some point, I would like to drop more R compatibility and focus on Julia-style names. But we originally tried to make it look more like R. And so there's a bunch of names that are exactly redundant. So size something 1 is going to be the equivalent of getting the n row. And we have both of them. Yeah, we need to do a little bike shedding there for sure. This is something that just will tell you which rows have NAs and which don't. This is really important for statistical analysis, but is otherwise maybe not so interesting. So let's move on, because I think I'd like to see, yeah, so can we go on one more? Hopefully it's there. Nope. All right, well.
By the way, is 8 minutes enough for lunch? And if you still have a few things, maybe we could also spill over after.
I would just like to see a few more things, basically. So can we skip a little further? I'm going to sort of pass over a bunch of stuff and show you sort of the reason you care about identifiers is, no worries, let's just sort of skip a bunch of this. So you can see these slides if you're into it later. They have a bunch of functionality you'll care about. These things matter. So this is these vector and matrix conversions. And I showed you earlier there was a way of turning something into a matrix and something into a vector. By default, what they're going to do is sort of a smart type thing. For vectors, that's very easy, which is just convert it to the type that it's the container of and see if it works, and if it does, it fails if there's an NA. But if you actually say any, it'll convert into a vector of NEs, and this will allow the presence of NAs. Move on to the next one, though. I think much more interesting is this sort of matrix thing, because this is really the nice way of taking a data frame, which you read out of some some spreadsheet that you stored as a CSV file, and then now you do matrix. And matrix, what it's going to do is it's going to look through all the types of the columns and find some columns, sort of the tightest thing it can do that will still store all of them. So matrix of all of them gives you an any array because you have to be able to represent all of them. But 2 to 5, for instance, here,
How do I do this?
Iris of 2 to 5. So it's
Oh, I see.
you're gonna take iris of 2 to 5. Yeah. And this is going to give you a float array. And so this is really the magic of saying, I now drop these things into standard Julia types, and I can do computation on them. So it's, this is really useful, but I think that sort of the reason I cared about the identifiers, move on a little bit, is this kind of magic. And so, another way of thinking about data frames is also a very different way of thinking about frames, which is, in some sense, they actually provide like an alternative namespace in which you could evaluate expressions. And that's exactly what's happening here. And Julia makes this really nice because it lets you manipulate expressions easily with this colon operator, which will allow you to quote easily some expression, and then you can evaluate it. And so here what we do is, with iris, quote an expression, and the expression is petal length, and this is like a Hadamard product of vectors, petal length times petal width, and this is going to give you effectively some sort of area of the petals. And I think this sort of thing is really what you really sort of the power of having these things, which is now you can evaluate in the special context of your data set all sorts of complicated expressions. And I personally am really fond of this thing, which is why we built it in. And this is, mentioning earlier, why you need to be able to clean the column names and make sure they're identifiers, is you want to make sure you can write nice expressions this way. If we go on to the next one, hopefully.
Well, why would you do this instead of just petal length times petal width?
Because those names aren't visible.
Yeah, those names are
Oh,
not
those are
in.
inside,
Those are
the
stored
dataset.
inside the data set.
Okay.
Right now it's just like a name of a column.
So you're taking an expression and passing it
Yeah, exactly.
inside the data set.
Yeah, so
Okay.
so what happens is the expression is now evaluated as if you had variables in whatever namespace that were the names of all the columns. And so this is like, you have 10 different data sets, you can now evaluate things that have same names and see different values. So this is,
It started out in S bar that you would attach a data frame, or generally a list, and that would put it on the search pack for names. It would put it at the head of the search pack. But then that corrupts your evaluation unless you remember to detach. So we came along just to put it onto the data frame, evaluate the expression, put it onto the search path, evaluate the expression, take it off the search path.
Okay.
yeah, and so I think, let's go like 2 more into this, but I think, basically, no, don't worry about it. I think I'd rather sort of let people, if they have questions about this stuff, see it. My sense is most people here are programmers, so I tried to sort of give some background to this stuff so you could see why you would care. But having known that you care, there's tons of stuff you can do. This is just a way of doing it within, and so you can do assignments. Let's skip ahead a little bit. These are, I think, when you start to be like, oh, this is really cool that you can do this. So you can do subsetting of the data sets, you can do merging of the data sets, you can group them, and so these are sort of operations to be very familiar if you're used to using a database. So this, for instance, is how you subset the iris. So you're only going to get the rows in which the species column is equal to the values of TOSA. So this is your like select operation from SQL. And you can see that works with the n-row. Here I'm just going to make 2 data frames that have columns that have some shared values in A and B. Yeah, let's paste that in. And I'm sort of going to go through it fast and only show this one and the next one. And so let's just sort of quickly look at it. So, A overlaps at values 1 and 2 and doesn't overlap at other ones. And so you might want to do with some sort of joining operation, and that's what merge is. And so on the next, so actually let's just write it. Merge df1, df2. And so what this is going to do is it's going to do what an inner join. And it's going to look at the values in the column. And what it's going to do is, by default, it's going to assume that if you didn't specify a column name, there must be only one unique column name shared by the 2. And it's going to look at that. But you can also do merge df1, df2, a. So comma, quotes a. And this is the exact equivalent of that. And so this is an inner join. If you do after this a, you do now comma left. So in quotes left. Now you're going to do a left join. So just, hit that. And so what it's going to do is it's going to figure out, do you exhaustively use the things on the left, exhaustively the things on the right, the intersection, or the union. You can also try right and outer. I tell you right now that right is not right, but outer is slightly broken. So outer actually correctly does it, but then prints out the wrong things that were only on the right-hand side. We're going to get that fixed before the end of the day. That actually got broken at the end of the night. So,
So we did all these, right?
Yeah, so we showed all these merges.
Why do you name these merge and not,
Join.
SQL things like join?
So join, the problem is that join already means something very clear in Julia, which is this string joining operation. And so we didn't,
SQL join and SQL this and SQL that.
so it might be nice. So the other reason is that R has this tradition of calling it merge, which is where it comes from that tradition. But I think there are strong arguments to making it something like SQL join. So that's merge. The next, hopefully one more, and I'll sort of stop here. Go on a little bit, is the split, apply, combine strategy. So this is, I think, a really great paper written by Hadley Wickham, sort of expounding on an abstract way of thinking about how you process data, which is you're going to split it into groups, you can apply some function on all of them, and then combine them all back. And if you know how MapReduce works, this is sort of a familiar paradigm. And go on one. So let's do this thing. This is going to take a little while, so let's start it, and then I'll talk about what's going to happen. So
Should I start loading?
yeah, do this. So this is going to load this movies data set. It's actually quite small in some sense, but our CSV writer is still a little inefficient. It's actually, to be honest, inefficient because it has to handle UTF-8 correctly, which it was not doing for a long time. And this data set has a bunch of UTF things.
Can you go back to the slide? Because I'm trying to do
Oh.
this at the same time.
So yeah, let's just, can you up arrow on this? Yep, so this command, do this. So this is how you're going to load this movies data set. So this is data ggplot2 movies. You're going to eventually wind up with this thing with 50,000 rows in it. And then this is the thing that I think is really cool. So let's run it, and I'll explain what it did. So by movies, year, and row. So what's going to happen is it's going to take all the rows of your data set, which are specified as movies. It's going to split it on unique values of the thing specified here, which is year. And then it's going to do some function operated on every one of those things independently. And here, the function it uses is called the nrow function, which tells you how many rows. And so this tells you how many movies there are in this data set for every year. And if you go up, there's pretty striking stuff. Like if you go all the way to the top of this thing, I was pretty amazed to discover that there's actually a movie made in 1893.
So nrow is a function handle?
Yeah, nrow. So nrow is an actual function. So it's just the name of a function. You can pass the name of a function. Actually, anytime you pass a function will work. So you can pass nrow the name of a function. You can pass an anonymous function. You can pass a function that's like totally defined explicitly there. A bunch of different ways of doing it.
Yeah, a function by itself is just a value. There's no special notation to get
Yeah,
a handle or
the
anything.
whole at prefix that MATLAB uses for MATLAB handles doesn't, we don't do that.
So is this the combine here?
So
nrow is the
no, so
combine.
nrow is actually, so the combine is completely implicit. So what actually happens is, let's do one more example to see it. So let's go back here. And then now let's make this a vector, and vector will be at the start of it action. So like square bracket. This is it
Which one?
right before here, like right before this thing, square bracket,
Okay.
and then action. I think has a capital A, but then it's the word action, and we have to put it in quotes also. Oh, sorry. This is actually another column, so we're going to make this a quote mark.
String of action.
Yes, exactly. It's a string of action.
So it's double quote before the A.
Yep, double quote before the
Put
A
word
and after
action
it.
in quotes. Yeah, there you go.
Yes, exactly.
But take out the parentheses.
What are you doing, bro?
Yeah, let me tell you this one fast.
It's just the names of two columns.
Oh, I see.
Yeah, and hopefully these are spelled correctly. Yep. All right. So now you get sort of much more interesting things where you can slice and dice these things. And there's another column in this data set which tells you whether or not this movie was an action movie. And so now you quickly have some sense of how many action movies and how many non-action movies there were over time, and so get some sort of changing trajectory of these things. And actually, I think
We'd like to do that with a general cross-tabulation idea. I'm just having a little difficulty deciding what the ultimate form of a table should be.
yeah, and
Is
also
that something that has, columns, rows, perhaps it's a three-dimensional array, but you want to be able to label all of these dimensions. It's not an insurmountable problem, it's just unfairly.
it's definitely worth. I think this sort of thing is really worth debating. But so I'll stop there and just see if people have questions. There are tons of more slides if you're interested about trying to explore the data frames. At the end, I have a bunch of suggested exercises where first you just use the data arrays and data frames, and then also you can do some sort of very basic statistics and machine learning stuff. So there's k-means and k-nearest neighbors and decision trees. These have been implemented, and you can play around with them and see how they work. And the reason that they're really fun to work with now is that you can just get some data set in a CSV file and now start applying these techniques off to whatever you're being given. But I think that gives you some sense of what it is. It's basically a very simple way of representing a sort of a relational database in memory in Julia that you can read out of disk or you can generate in real time and do a bunch of things like select operations, join operations, grouping operations, all these sorts of things. I think that's the power of it. And it's amazing how easy this was to write in Julia, which is, I think, the thing that's really to be said about Julia as a language is this code is quite readable. It still can be a lot shorter and cleaner, but it's like surprisingly small to implement this functionality, basically because Julia has really nice ways of expressing the things we needed to express. And I think writing it in a different language would actually be quite difficult, especially a language that would make it difficult to express types would make it extremely difficult to articulate the concepts of heterogeneous types and things like that. Okay, so I'm just going to quickly just sort of touch on a few questions that people asked me about, and some of these sort of happened while I was talking, and this also summarize again. So one is thinking about how you deal with really, really large data sets on disk in some mechanism or other. And so one we already talked about, which is this idea of streaming data. And there is already a mechanism called data stream that's in the data frames package. This is much less well developed than data frames in general, but it is a mechanism. And what it will do is that you will say, I want to treat this source of data as a stream, and I want to draw at a time a mini batch of size n. And what that means is that every time it looks at the stream, which could be standard in, but it could also be a file on disk, it will pull out an n-row data frame and then pass you back that. And so this is the really easy way of dealing with a data set that's far too large to store in memory. Touching on that, but sort of going deeper, and I think is much more interesting in some sense because it's more challenging, is thinking about how you can interface nicely with a database. And so someone recently just started making a package for ODBC. I don't know how robust it is yet, but sort of as those develop and we get more ability to deal with databases in Julia, we'll have way, way more ability to start pulling data out of a database. And one of the things that people have already started working on, I think probably a few more months till it actually is useful, is having the data frame interface to a database. So you just say, SQL data frame and give it the name of a database, and it will now let you use the API for a data frame and just transparently treat the database in the same way. I think that's still a ways off, but it's something we're definitely working on. I think another question people had is actually a much more broad Julia question, which is, how much of this redefinition of things like SVD are we getting for free, and how much are we not getting for free? There's a lot of things that we're getting for free, but things like SVD we're not getting for free. And there's sort of two questions here. One is that actually for a data array that has missing values, you actually do want to run a different algorithm than the standard SVD. But even if you didn't want to run a different algorithm, there is a complexity about whether the algorithm you're dealing with is something written in Julia, in which case it should be written abstractly enough that you can't override it. And that's like how sorting is done in Julia. It's sufficiently abstract that you can't override it, and things that are actually being called into BLAS of some sort, those things we can't just override. And so the SVD in data frames and data arrays is an example of something where we are actually just having to pull down into this black box of C code and then do some post-processing. We're not getting sort of magical NA propagation. If, in contrast, someone were to go through and write a super, super fast implementation of the SVD in Julia that used abstract multiplication and addition, then we would be able to just propagate the NAs. And maybe one day that will happen, but for now, sort of that kind of thing has to be redone for data frames, and whatever structure you're going to do, you're also going to have to do that for. And those, I think, were the core questions. If anyone else has a question, I'll answer it now, or I'll just sit down and let the next part start. All right, great.